So let's start. Welcome back. Hope you had a good weekend. So I put some iClicker, like one iClicker question. Almost half of you have answered. Let me mute my. Okay. So some announcements. One is that exam 2 will cover lectures 9 to 16. One of your friends say that the study guide extend beyond that because initially I planned the exam differently. So I need to trim. I will trim the study guide and upload a new one either today or tomorrow. Second, there is this persistent question about Canvas versus others, meaning like others can be the grade book that I prepare and email you, can be Perusal, can be Pearson. So others, Canvas, like all programs, they have bugs. So sometimes the synchronization between different webwares are not that good. That's the reason why we use our own gradebook. So if there is any discrepancy, you should email me, but your first, if you want to go ahead, always go with others. Meaning, one example, if the due date for homework, I don't know, 4 is different between Canvas and Pearson, you should go with Pearson. Because sometimes we change Pearson, we change the deadline on Canvas, and Canvas basically revert the deadline into the first deadline that we enter. Okay. So today we will talk about electromagnetism. Yeah. It's a difficult question because not all questions are equal. Sometimes I split the question into multiple. So it will be 14 points, but the number of questions can be more. You can view of it as 14 points despite, let's say, there are 20 questions. Okay. But if you understand the material, whether the exam is easy or difficult or just right, you should be able to get good grades. That's the goal of my exam, to evaluate your understanding in my teaching. Okay, so let's start. So last time I show you a famous experiment by Oersted, and I use the drawing from your textbook. Okay. So doesn't work. Okay, good. So the drawing of your textbook, which is there is a wire and a compass, and then if you have electricity, then the compass will rotate. The compass needle will rotate. So here, I hope you understand that the wire is under the compass. Is that clear? Who's not clear with this, that the wire is under the compass? Because last time somebody asked me this question. So alternatively, in the exam, I can choose similar figure from your textbook that draw like this. That means here, the wire is on top of the compass. Okay. Similarly, you know, many of your pre-meds, DNA is, sorry, DNA is a right-handed helix. People draw it like this. That means this strand is in front of the other strand, right? It's a right-handed helix. So it's not different than drawing DNA. So Oersted did this experiment in 1820. And despite his being Danish or Dane, people recognize that what he did was really profound, which is he generated magnetic field from electric current. So we have electricity and magnet. magnetism, and Oersted show that a flowing charge or a flowing current can generate magnetism. And then people quickly realize that his name will be immortal. So, and then people, including Faraday, recognize the importance of Oersted's experiments. Then what they're trying to do, which is the essence of the Eclicker question, is that can we generate electricity from magnetic fields? So one person that get credits for this invention or discovery is Faraday. And then it takes, do you know how long it takes from Oersted to Faraday? You will see the experiment is really simple. How long do you think it took Faraday to discover that he can generate magnetism from electricity? It takes more than 10 years. Right? So for us, it seems silly that the simple experiment that you will see takes the whole humanity 10 years or more than 10 years. It's half of your age. It's half of my age. But it is silly because we have seen it so many times. Okay, so that's the subject of our lecture today. Or should I grade this? Maybe. I'll do this. Oh, I need to stop. Sorry, I cannot. Good. All right, so next, these are the plan. So the plan today, this week, we will do lectures 18, 19, 20. My plan is to finish magnetism by the end of this week. And after the spring break, it will be a clearer cut. We will do optics. Okay. For some of you who think that this topic is not for you, maybe you will find optics more suitable or better match with what you like. All right, so next I want to recap a few things. One is Ampere's law. I don't remember, I think there is this accent somewhere, maybe here, or maybe I shouldn't do anything. Ampere's law, which is, this is similar to Gauss's law, which is a way to find magnetic fields without doing complex math, okay? So the example that we try, that we show you is infinitely long wires. And we know if we have infinitely long wires, the field will look like this. Well, we don't know the arrow for now. But since you're smart, if the current flows from bottom to top, then the field looks like this, right? And then Ampere's law is basically the parallel component, which means this component, just be parallel. This is also be parallel. At this point, the sum of the parallel component of the magnetic field over all length is equal to mu naught times I enclosed. Okay. So here, what is I enclosed? So if I say I is, the current is I, then the I enclosed is I. But if I have, let's say, if there is a surface and there are two wires, one points into the surface, the other one points away from the surface, then the I enclosed is any guess? 0. Good, Hannah. So so this I enclosed is not the magnitude, but the net. I guess if you want to be more exact, I net, but no one put net on the symbol right there. Okay. So for doing this problem, you need to know the symmetry, okay? So the reason why we choose this line, so this delta L here is a circle, because if you have a wire and then you move around the wire in a circular path, it looks the same. This is why we choose circle. And we did this last time, which is basically B times 2 pi R, because the Amperian loop or Amperian path or just a closed path is equal to mu naught I. Okay, so B for a line is mu naught I times 2 pi R. So we have done this last time. Okay. Any question? This is just a recap. Next, we ran experiments. So I want to be completely transparent to avoid surprises. We derive this equation. What I mean by this equation is, so let me first set the problem. So we have two parallel wires. Okay, and let's say the flow, the current point, the two currents points towards the same direction. It can be I1 and I2. And then we figure out the direction of the magnetic field, which is like this for the top one, and the bottom one also the same. And we arrive at the force on cable 1 due to cable 2 per unit length is equal to, there is mu naught somewhere. It's basically mu naught 2 pi R times I1 times I2. Okay. So I still haven't finalized my mind. I still haven't made up my mind whether I will put this formula on the cheat sheet. Okay. Because I respect you. I think all of you will be able to do this derivation. It's like 2 lines. Okay. If I think you're not smart, I will put the equation. But so just to be safe, you should learn how to derive this equation. Don't expect that equation to be on the cheat sheet. Okay. So that's one. So this is the force on cable 1 due to cable 2. It is proportional to the current 1 and current 2. So the current that you flow on the top cable and the bottom cable. So this one is F12. Okay. You can divide it by L. So, but cable 2 also experience the same force. Let me take it back. The force from cable 1. So I call it F21 divided by L. Now the question is, which one is larger, F12 or F21? Or are both of them equal? Okay, so F12 is equal to this expression. F21 is, if you do the derivation, you will end up with this expression. So which one is bigger? So they are the same, right? So this is another manifestation of, this is similar to Newton's third law, which is the action to one object will lead to equal, I guess, counteraction to the other object. So this two force is equal. So you can, let's say, put 1,000,000 times larger current on the first cable, but the force that these two cable experience, they're the same. Okay. So that's the only thing that I want to recap from this, from parallel wire. Any question? Now we move to solenoid. So solenoid looks like this. Looks like this. Basically, you have a wire and then you fold it like concentric circles. solenoid. So so you have basically you can draw it like this. Okay, good. And this one you can view it as a series of circles that are coaxial, meaning they are concentric. I don't know how to say it in normal English. Okay, they are parallel, they are aligned, and they have the same. They have identical diameter. And the drawing on the exam or in homework will be better, so you know which one is in front. Let's say this one is in front, then everything should look like this. Then you know whether the current is not perpendicular, clockwise or counterclockwise. And then one thing is that if you have a circle, like let's say this this loop here, and then let's say the current flows clockwise, right? It's clockwise. If you view it from the other side, it will be counterclockwise. This is just common sense. Maybe not as trivial, but if you do it with plates or with anything, it's always always the case. Okay. So on the exam, I will say, you know, when you view from the right end of solenoid, let's say, I may phrase it that way. The current will flow clockwise or counterclockwise. Okay, so this is what we call solenoid. And we know from a single loop, the field looks like a bar magnet. Okay. So if you add many loops, okay, then because of superposition, what survive is the field at the center of the solenoid. So there is no field outside solenoid, and so all the field will be inside. Let's say if the currents flow this way. Okay. I have this demo that I set up. I set up by myself this morning because our team was busy last weekend helping university for the open door events. So I have this solenoid, looks like the one that I drew on the whiteboard. And here is a secret sauce. I'm not, sorry. This is not secret sauce. This is a magnetic powder or magnetic, what do you call, sand. So as you can see, right now, there is solenoid with current or electric currents I is equal to 0. Okay. And I'm going to turn on the electric field. So basically, after I turn this thing on, there is currents, and I want you to see the field. See, did you see? So the magnetic current outside didn't get affected by solenoid, but the field inside is nicely aligned, just like what I drew right there. Okay. Any question? Questions? No? Everything is clear. So the reason why I did recap on Ampere's law, because we want to use Ampere's law to derive the field inside a solenoid. Okay? So the equation that you will see will appear on the cheat sheet. So one thing, okay, so first let me draw it differently. Okay, what I'm gonna do is I'm gonna take, so this solenoid, I'm gonna take cross section in the middle of solenoid. Okay? So what you will see is I'm sorry if it's the opposite from, yeah, it's the opposite from your, it doesn't really matter because if I want to keep it the same like in the notes, I need to flip the arrow. But let's stick with this representation. So basically, we have a solenoid. We slice the solenoid we view the plane in the middle of solenoid. Is that clear? You guys still remember this representation? So this one, basically the wire goes into the whiteboard, and this is so like this. And this one here is points towards you. All right. And so basically, if you want to connect it with wire, you can. Now back to the Ampere's law, which is the sum of the parallel component of magnetic field is equal to mu naught I. You can put net if you want, and close. Okay. So first, let's do one case because I just gave you the fact that the field outside a solenoid is zero. So how to do that? How to figure out that the field out? Okay, first, how do we know that the field outside the solenoid is zero? What I mean by that is the field here is zero. How can we show that using Ampere's law? Yeah, you. Yes, you. Yeah. You said you love physics on Saturday. Okay. Who else love physics? People at the back. How to show that the field outside the magnetic field is zero? I think I have this toy. Doesn't work? Oh. How to show that the field outside the magnetic field is zero? Outside the solenoid, sorry. Okay. So perhaps my teaching is not good enough. So I always blame it on myself. So let's say this is the path. Right now the path is in blue. Delta L is in blue. We know that there is no component of magnetic field inside, so we can even number the path number 1, 2, 3, 4. If you sum if you connect all the path, it will be closed path. Okay. The contribution of the parallel magnetic field on path 1 and 3 is 0 because the magnetic field is not parallel to path 3 and path 1. Okay. So right now, B parallel in path 2 plus B parallel on path 4, right, is equal to mu naught I enclosed. But what is the enclosed currents here in this surface? Two of them points towards the whiteboard and two of them points towards you. So the sum is 0. This is like somebody put a water hose towards the whiteboard and somebody behind the whiteboard use a water hose to and points at you. So the total is 0. So this one is 0. Therefore, one consequence is that one solution of the equation is that there is no magnetic field outside the solenoid. Okay, so that's just to show you that with Ampere's law, you can get some insight into the magnetic field outside the solenoid. Now I'm going to change the path. So it will only go halfway. So from the center of solenoid to outside solenoid. And I'm gonna try to use the same numbering. So 1, 2, 3, and 4. Okay. So we know that the parallel magnetic fields with respect to path 2 and 4 are 0. And we know that the magnetic field outside a solenoid is also 0. Then B, the only one that left is B. So this is due path 2 to path 1. Okay. And then equal to mu naught I enclose. Okay. So I want you to be careful with the I enclose. So what is the I enclose here? Amanda, wake up. What is the I enclose? In this, I have this area. What is the I enclose this area? Is it I or 2I? 2I, okay. So here is 2I, but I'm gonna say I'm just gonna say N. N times, sorry. I need to have equal sign. Mu naught I, mu naught N times I. But that means B. So, okay, so first I need to define N. N is equal to total number of turn. Okay, that's capital N. And then I made a mistake here because there is delta L, and I will define L as the total length of the solenoid. Okay. So B is equal to mu naught N times I divided by L. And then if we define turn density, if we define small n as turn density, then this is the solution for the magnetic field inside a solenoid. So N is turn density, which is equal to capital N divided by L. Okay. Good. Any question? So that's solenoid. I think there is a iClicker question. Did I skip that? Okay. This one, I hope the screen is good enough. Okay. So this is taken straight from your textbook. And then I'm not the one who drew this. So you need to pay attention to the way your textbook draw the solenoid. Okay. If I draw it, I would make it less dense, but this is from your textbook. So there is this question, and I'm gonna redraw it here, so it will be clearer, hopefully. But let me just read the question. So we have these two batteries, so I'm not reading it obviously. So the question says, aligning a bar magnet. A bar magnet is suspended freely here. The cursor doesn't appear. So yeah, the bar magnet is the one with N and S, freely in line with the long axis of a solenoid, as shown in the figure above. If the magnet aligns so that its north pole, capital N is not this N, but north pole, face the solenoid, in which orientation A or B is the battery connected. So first remember that the direction solenoid is basically concentric or coaxial coaxial rings, and then the direction of the magnetic field follows the right hand rule. Okay. Do you remember that? So the direction of the magnetic field is the direction of your thumb. First, you need to use your right hand, and then the direction of the way you curl your right hand, or the direction of the rest of your right hand, is the direction of the currents. And then your thumb is the direction of the magnetic field. And then I don't list. So basically, A is A, capital A, B is capital B. There are two positions of the batteries. Okay. The question is which orientation of the battery is correct. Okay. And you can do this with your neighbor. Sorry. Oh, you're good. No, I'm good. I'm good. I need paper towel. What are you looking for? So I haven't drawn it, but let's see the results. It's good. So it seems that most of you answer A. Is it easy or confusing? Yes. Okay, good. Well, not good, but so the solenoid looks like this. So this, if I'm the one who draw the problem, or if this problem appears on the exam, it will be something like this. Okay. So basically, if the current points up, right? If the current points up, then the field will point like this. But if the current, I'm gonna do something that's physically impossible. If the current points like this, then it will be like this. Good. What else? Did I miss anything? And then the field north and south. So this one, okay. First, let me, okay. So, and then the direction, the question is whether A is like this or B. Okay. Here. Okay. And then if you have magnetic field or a magnet bar, the field looks like this, right? From north to south. Okay. And then the problem says that this bar is suspended freely on a string. So if the current goes up, then it will repel North Pole and the South Pole will be here. Okay. Because the field repel. So the correct answer is the blue one, which means that the current goes down. Sorry. The current goes down from this part of the solenoid. So the blue one is the correct one. So the answer is A. Okay. So 85% of you got it right. So that's really good. So maybe I shouldn't spend too much time on this. Okay. Any questions? Good. Yeah. No, we have no, for this one we use how electric current generates magnetic field. Using this way? Okay. So if the direction of the current goes like this, right? From this points towards you, then the field will be the black one. But if the direction of the current goes into the field, the whiteboard, then the the magnetic field points the opposite direction. So here, and then like this. Okay, yeah, good. Gabe, no, you. I thought that. The blue one. Sorry, the correct one is the blue one. This black one is just a way for me to think about the problem, but the correct answer is the blue arrow, which looks similar to black arrow. Good. Has been a while. So if you have a battery, and let's put a resistor here, the current goes from the positive electrode or pole, an electrode, to the negative electrode. So the answer is A. Okay. All right. So yeah. Oh, you can. Oh, if you flip the battery, then it will be the opposite. Oh, that's the thing that the question is testing you, which is you. So this problem asks you for your understanding of the multiple aspect of the class. One is where is the direction of the currents. Second, if the current flows clockwise, where is the direction of the magnetic field? How about if the current flows counterclockwise? Where is the direction of the magnetic field? You cannot assume that. All the question give you is that this is the steady state orientation of the freely rotating magnet bar. Oh, because the North Pole points this way. So on the exam, I can say I can give the direction of the position of the battery, I can say is the position is either A, B, or C, let's say. Right. And then if the battery is in A configuration, then north is closer to the solenoid. Yeah, so in order for two things to interact, to attract the field, so this one is repulsion. Maybe this is something that we haven't emphasized. This is repulsion. Similarly, if you have two positive charges, this is the field of two positive charges, and we know that charge with the same signs, they repel each other. But here, the reason why the steady state orientation of the bar magnet is like this, because there is attraction between the solenoid and the magnet bar, and the bar magnet. Oh, the problem tells you that. And this is I copy and paste from the textbook. Good. Okay. So next is toroid. So toroid is basically solenoid that looks like a donut. Just a relevant topic for a morning lecture. So I'm going to switch the camera to this camera right here. So solenoid is the one that you see here is basically, no, not solenoid, toroid. So anyone knows why we work with toroid? Is it just for exam 2? So the thing is with solenoid, there is what we call edge effect, meaning the field at the end is different than the field in the middle, right? Let's say it points up. Sorry, points up. Okay. But with solenoid, we keep all the fields inside. Sorry, with a toroid, we keep all the field inside the donut, inside the toroid. So now I want you to appreciate that the direction of there is no preferred orientation of the magnet powder. And then I'm gonna turn on the magnetic field. So 1, 2, 3. It's not the strongest magnetic field, but you can see there is this lines here that forms a circle. And if I do this, it will be even stronger. Basically, this is like making this basically like similar to adding temperature to the system. So you see the circles. Good. So back to a little bit math. The math is fairly straightforward. So for solenoid, B is equal to mu naught n divided by L, or we call this small n, times I. But B for toroid, L, so L for toroid is, what is the circumference of a circle? What is the circumference of a circle? 2 pi r. Okay, good. So I know that many people are sick these days, but so first, if you are sick, you can join by Zoom. So that's one. Second, If you're not sick, then you need to participate in class, okay? So mu naught n divided by 2 pi r times I, which is what's given in the last formula right there. Okay. Any questions? Okay. So let's just recap of what we have learned so far. So right now, what we do, what we have done is working with constant electromagnetism, meaning the current doesn't vary, the magnetic flux doesn't vary. And for electric field, this is for electrostatic. We learn about Gauss's law, which is the electric flux times area, Gaussian area, or just area, enclosed closed area, is equal to Q divided by epsilon naught, or 4 pi K times Q. This is enclosed. And today we learn in magnetism that we can use Ampere's law, okay, which is the sum of the parallel component of magnetic fields around a length is equal to mu naught times I enclosed. Do you know why one of them is perpendicular, the other one is parallel? I forget to start with that. So for electricity, the field can either go out of or points to a point. So positive and negative, the field points towards the charge. But for magnetic fields, the field always returns to the origin because there is no magnetic monopole. Okay. So that's the reason why one of them is perpendicular, one of them is parallel. Okay. And just to complete our discussion here, if we sum the potential drop along along closed path, what is the answer? What is this equal to? The answer is actually right there. So this is one way to write Kirchhoff's law. So E times delta path along a closed path is not equal to mu naught I, but for electricity is equal to 0. And to complete our knowledge for constant currents and constant magnetic flux, the sum of B over an area, a closed area, is equal to 0, which means there is no magnetic monopole. So you know what's coming, which is we're not done because once you think that you have a complete understanding of electromagnetism, somebody runs different experiment, blame it on Mr. Faraday. So we will discuss about Faraday's law, Lenz's law on Wednesday. All right, have a nice week. Hey, what's up? Hey. My name is Eli. I look like